And so if we look at the derivative, the area between the two curves here, we're looking at this area. This is the left boundary. The right boundary would be up here, and I apologize, I didn't quite give myself quite enough screen. But this would be the area right here. And we said that this was 20 over 3 units squared. Everyone see that? That's the area between the curves. Now compare that to this, this one right here, this graph right here, is y equals x squared plus 1 minus x. This is the difference between those two. And so if you evaluate the area under that single curve with the same boundaries, okay, here down to there, and here down to there, see where this goes here? And you take a look at this area right here, just by looking at it visually, it looks like it's pretty close to the same area, isn't it? It covers about the same amount of screen. Now this is very qualitative. But the area of this, after we did our math, was also 20 over 3 units squared. So there's just a little visual sort of confirmation. It's not a very good proof, but if you were to actually visualize that, you could see that those two areas, the one in pink there and the one in yellow, that those two areas are pretty comparable. And we've algebraically sort of proven that they're the same. And here you go, there's sort of graphically, we can kind of see that they're pretty close. Now a couple things that you're going to have to pay attention to. Okay? If you have an example, let's say like this, where you have, okay, here's function 1, okay, f of x1, and you have f of x2, like this, okay. You have to be careful if we're talking about this interval right here, between there and there, and we're looking for this area between the two curves, you have to just be careful to know that this is function 1, and this is actually function 2. If we're talking about, which one is the greater, right? So you'd have to do this function, you have to realize is on top in this interval. So you'd have to have some knowledge of the graph. And if you wanted to take a look at the areas between these two from here to here, if you want to look at this area, then this is the function that's function 1, right? And this is function 2 because it's underneath. So you have to be careful there. And the trickiest part is actually if you're looking for the areas between the curves where they flip-flop. So you're looking for the area between the curves here and here. You see that? In this case, you'd have to do 2 separate calculations. And the most important part being you have to find this intersection point. And that's the point that's going to be sort of your cutoff, right? Literally. So you got to do, here's A, here's B, wow, this is going to be C. So you have to treat this as the upper function between A and C, find that area, use this as the upper function between C and B, and find this area, and then add them up together. Alright, so in your textbook here, this is example 3, and this would be an example where you'd have to do some digging, right? You'd have to figure out, okay, which is the upper function, which is the lower function, and where's my intersection point. So if the question asks you to find the area between the curves y equals sine x and y equals cos x from 0 to pi over 2, then, you know what I mean, you're going to have to do some digging. Now, you know a little bit about what the graphs look like. You know that generally, even if you didn't have this diagram, you know that sine goes up like this, and the cosine, starts to go down like this, right? And so where's pi over 2? Well, pi over 2 actually is right here, right? A quarter of the way through each period. And so you are looking for this area and this area. So you would have to sort of have some idea, whether you graphed it on your calculator or did some points or whatever, you'd have to understand that, hey, this particular interval I have to split that up into two sections. And that's what you would have to do here. So here's the diagram given for you here. And this intersection point is pretty important. And if you recall your unit circle, okay, the unit circle, again, some knowledge of the unit circle and some memory of the unit circle here. This actually you almost should know without even looking, right? Like, where does sine, the value of sine, equal the value of cosine between 0 and 2 pi? Well, 0 degrees here and 2 pi here, I'm sorry, and pi over 2, I should say, right here in this, they're the same at 45 degrees or pi over 4 radians. And so if you, oops, wrong class. Right. If you take a look then at this diagram, you know that the intersection point must be pi over 4. And that's kind of where you start to calculating each individual area. Okay, so if it's been established that pi over 4 is your separation point there, then let's calculate R1. Okay, so the area of R1. Well, cos is the upper function, isn't it? Okay, so let's find out one function. Keep doing capital. One function that represents, the combination of these two. So let's do cos of x minus sine of x. That is the one function that we can look at and say, hey, I'm going to find the area under this one function. It's the difference of the two functions, with this being the function with the greater values on this interval and this one with the lesser values. And so capital G of x. So we find the antiderivative. What's the antiderivative of cos? Is it negative sign or positive sign? It's going to be positive, yeah. So it's going to be positive sine of x, and you don't actually need that bracket there. And the antiderivative of sine is going to be negative, so that's where we need a negative there. So that's like a plus cos, sorry. Positive cos x. Okay? And we just have x's in there. We don't have to do anything fancy and all that. That should be just it there. We good? Does that look right? Okay. Now I'm going to show you some notation that you probably wouldn't know. And this evaluation of the area, I'm going to show you. If you write it like this, okay, with kind of a large square bracket to the right of it, some the textbooks you'll see on both sides, but if you put this large square bracket here, and you put the boundaries, so like pi over 4 up top there, and then 0 underneath there. That means that we're going to evaluate this between 0 and pi over 4. So to find the area of this between 0 and pi over 4. And this is notation basically saying that you're going to do this. You're going to do sine of pi over 4 plus cos of pi over 4 minus sine of 0 plus cos of 0. Okay, that's what this actually means. It's an evaluation with this difference. You're finding the area under the curve, really. So sine of pi over 4, I'll flip to kind of white here. Sine of pi over 4 is what? What's sine of pi over 4? So on that unit circle, that was root 2 over 2. Very good. Plus cos of pi over 4, also root 2 over 2. Very good. Minus, okay, what's sine of 0? It's going to be 0, isn't it? And cos of 0, 1. Yep, very good. So we have 2 root 2 over 2, which is just going to be root 2, minus 1. Root 2 minus 1. Okay, for this area right here, that's area 1, region 1. Okay, agree with that? Good with that? Okay. What would you guess to be this region, or what would this region, what does it look pretty close to being? It looks pretty close to being the same thing, doesn't it? Yeah. Why don't we just confirm that? I mean, it looks pretty close, and you can probably logic your way through that, right? Reason your way through that. But if we did sine of x, okay, which is now your upper function, right? This is sine, minus cos of x, and took the antiderivative of that. So if g of x was now sine x minus cos x, and we took the antiderivative of that, what would that be? The antiderivative of sine is negative cos x, and the antiderivative of cos x would be positive sine x, which is actually what? Well, we could factor a negative 1 out there. What do we want to do? Sine x plus cos x. Okay, yeah, so look at this. We have sine of x plus cos of x evaluated at, this was the first area, pi over 4 minus 0. Now we've got two different boundaries here, right? And so it looks like it might be pretty close to being similar. But, you know, if we did negative 1, and then evaluated this, cos x plus sine x, right, at pi over 2 and pi over 4, and if we follow that through, let's see what we get. So if we fill in these values here, yeah, cos of pi over 2 is 0, sine of pi over 2 is 1, and cos of pi over 4 and sine of pi over 4 are both root 2 over 2. This negative out here maybe throws you off just a little bit. It's like, hey, how can, you know, this be the same as itself without the minus? Well, it's because you're evaluating at two different points. And if you follow it all the way through, you end up getting root 2 minus 1 as your area, which is the same as the original area. And so we have root 2 minus 1 plus root 2 minus 1, and you get 2 root 2 minus 2 units squared. Okay? And as a matter of fact, because in calculus we use u extensively as a substitutionary value, we won't use that unit squared there. We'll just say the area is. You know, don't worry about the units. One more thing we need to cover here in this section. So if we look at example 4, if we have an area that is underneath the x-axis, okay, an area that's underneath the x-axis. Let's, you know what? Let's this example here. Actually, I want to go back to this example. So that's example 4. We'll come back to this. Okay, let's start with example 4. But I actually had this one prepared to explain to you, and it's back. It's way back here. Okay, way back here. So let me just kind of break down this example here as far as area goes. Okay, now this is the graph y equals x, right? And we did this in a previous class where we calculated the area between 0 and 1, right? And obviously that's a half of the 1 by 1 square. So the area is 1/2, right? Or 0.5. Now, if we did the area, if we looked at the area under the curve between here and the x-axis, okay, and we took a look at, well, what happens if we have, you know, this 0 as our right boundary and negative 1 as our left boundary, then what would happen? The area under the curve we know here should be, if we're just talking about this pink area now, the area should be 1/2 as well, right? So what do we get though? Area function is the antiderivative evaluated at 0 minus the antiderivative evaluated at negative 1. And so you get 0 minus 1/2. You get negative 1/2. Okay? So if you're looking for an area that is between, and when we say under, we've always said under